We're going to continue on with our application of thermo and take a look at Gibbs free energy and whether a reaction is thermodynamically favorable and what that means. And then what happens if it's under kinetic control, and then how we can take an endothermic reaction that requires energy and couple it with an exothermic reaction that produces energy. Greatest example of that is some of the reactions that are involved in cellular respiration. So we'll revisit a little bit of biology as well. And so a thermodynamically favored process is one that does not require energy from outside the system. There's some examples there for you to read, but the universe likes thermodynamically favored processes because it doesn't require additional energy. Thermodynamically unfavored processes require some kind of energy from outside the system in order to induce the desired change. So again, some other examples. Actually read through these examples because they are ones that commonly appear as part of multiple choice questions on the AP exam or as part of FRQs. Now, a process that is thermodynamically favored in one direction is not thermodynamically favored in the other. So hopefully that makes sense to you. So exothermic reactions are often thermodynamically favored. Nature tends to favor a process that causes a reduction in energy. And so if you remember, when we looked at enthalpy, we could identify an exothermic reaction because we would have a negative enthalpy value. Also, thermodynamically favored processes like an increase in the disorder of a system. And so we also like to see a positive delta S. There are some endothermic reactions that can be thermodynamically favored. Good example of that is evaporation or evaporative cooling. So basically you feel cold when you get out of a pool or something like that. As the water evaporates from your body, the water is actually pulling heat out of your body to drive an endothermic process. But then that is thermodynamically favored. Dissolving soluble compounds is also thermodynamically favored. For most ionic compounds, the temperature of the solution is going to decrease the dissolving process. As you know, you can dissolve faster and you can dissolve more. But all three of these reactions are endothermic, but they are thermodynamically favored. The one here, this C3H8 one, is actually propane. And so when your barbecue is on, basically if you feel the propane tank, there's a cold spot on the side of the propane tank where the liquid is turning into a gas at the liquid surface. So the next time you have a barbecue, check that out. So we can tell if a process is thermodynamically favored by looking at the enthalpy. Exothermic reactions are favorable, so a negative delta H, and also to see whether there's a greater degree of disorder, so a positive entropy. So there's going to be two methods. The first is to take a look at the change in entropy of the universe, and we'll review the universe, the system, and the surroundings in just a minute. And then the other way is to calculate the Gibbs free energy of the reaction. So just as a review, we have our system here, we have our surroundings, and then we have the universe. So the system is going to be the chemical reaction itself. It's the reactants and the products. The surroundings are going to be anything outside of the chemical reaction, the beaker, any water in the beaker itself, everything outside the beaker, everything in the room. And then the universe will consist of both the system and the surroundings. So when we're trying to figure out if a reaction occurs, we have to look at what's going on in the system, We have to look at what's going on in the surroundings and then collectively what's happening in the universe. And if the delta S of the universe is greater than 0, the reaction will happen. It may not be fast, but if the delta S of the universe is less than 0, the reaction will not happen. So the universe is expanding, therefore the change in entropy of the universe needs to increase in order to facilitate this expansion. Looking at entropy and enthalpy, basically in what happens. This is heat flow. So notice here in an exothermic reaction, heat is flowing from the system into the surroundings. And that influx of heat into the surroundings is going to increase the entropy of the surroundings. And so the change in entropy of the surroundings is positive or greater than 0. Versus an endothermic reaction, the heat's going to flow from the surroundings into the system. The entropy of the surroundings decreases, so the delta S of the surroundings will be less than 0. So if a process increases the entropy of a system, then the delta S of the system is greater than 0. It is exothermic, and so a positive delta S of the system will be exothermic and thermodynamically favorable. Looking at our second method for determining if a process is thermodynamically favored, we're going to look at the Gibbs free energy of the system. And Gibbs free energy is a formula that is on your formula sheet. It's going to include the enthalpy change and the entropy change of the system. So it's super important to pay attention to the units here. Enthalpy is usually given to you in kilojoules. The entropy change is commonly given to you in joules per kilogram. And so when we do math with this, we have to be careful to remember to change our joules here to do the conversion of joules to kilojoules. The other thing that might happen to you, you might be given temperature in degrees Celsius, and so it will become important to change that temperature to Kelvin before you use this equation. The units for free energy are kilojoules. Gibbs free energy is defined as the maximum amount of energy that can be used to do work, and it will combine both the enthalpy, or the energy transferred as heat, minus the energy used to create disorder. You'll often see something like this with this delta G with this little 0, and the way that's said is it's called delta G naught. And anytime you see this little naught symbol, that means standard conditions or standard state. And for it means we have pure substances, means they have a concentration of 1.0 molar and a pressure of 1 atmosphere. Commonly, these occur at 25 degrees Celsius, or 27, what is it, plus, we're going to add 273 to that, so convert that to Kelvin, right? So there are two ways to calculate the delta G. We can use the formula of delta G equals delta H minus T delta S. You may be asked to come up with that delta H a number of different ways that you know from thermo. You can use calorimetry, Hess's law, or enthalpy of formation of reactants products minus reactants. Calculate delta S using entropy values, which you did in yesterday's homework, and then we can use the formula. So let's take a look at that first. This one says to find the delta G for a reaction if the delta H is 218 kilojoules and the delta S is 765 joules per Kelvin, and 32 degrees Celsius. So we have to do a couple things before we can plug and chug into an equation. We're going to have to convert our temperature of 32 degrees Celsius to Kelvin. So 32 plus 273. We're going to have a 305, I think, Kelvin, 305 Kelvin, okay? And then we're also going to take our negative 765 joules Kelvin, and there are 1,000 joules in 1 kilojoule. And using the calculator then, that should give us 0.765 kilojoules per Kelvin. So then our delta G will be equal to our delta H, which is negative 218. It's going to be very important to keep track of your positive and negative signs. And then we're going to minus T, which is 305 Kelvin, delta S, which is negative 0.765. Really important to remember that negative there, okay? Kilojoules per Kelvin. And if you put all that in your calculator, you should get a positive 15.3 kilojoules. And based on that, we would say it is not thermodynamically favored, because it would only be thermodynamically favored if our delta G was negative. Again, it's going to become very important to keep track of your positive and negative signs in these kind of problems. This chart is, College Board loves this chart. And so thermodynamically favorable, I think you can see you'll get a negative delta G if we have a negative delta H and a positive. So a negative and positive, it is thermodynamically favorable at all temperatures. But notice these are different combinations of how you can get a negative delta G. And so very, very important. I'll star it, 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 I'll star it. So hopefully you can realize that this concept is extremely important. So a good one to either copy down onto a card and just kind of study and make sure it makes sense, or print it out and kind of study that way. All right, so let's do another example. It says delta H is negative 163 kilojoules, and delta S is positive 148 joules per Kelvin for the following reaction. Is the process thermodynamically favored? So now we can get in the habit of saying, hey, wait a minute, my delta H is negative and my delta S is positive. That's the nirvana of how to get a negative delta G. So yes, this reaction is thermodynamically favored because, and your justification would be that the delta H is less than 0 and that the delta S is greater than 0. And that's all it will take. Another way that we can calculate the delta G is to use the delta G naught formation values. And these are found in the back of your textbook. So hopefully you brought your textbooks home with you and can find those. So delta G naught formation is the free energy change that occurs when 1 mole of a compound is made from its elements in their standard state. And if we have an element by itself, that value is 0. So this equation is on your formula sheet, but the delta G naught of a reaction is the products minus the reactants. So let's practice with that a little bit. This says to find the delta G naught of the reaction for the thermite reaction under standard conditions. So this is the thermite reaction. And so if we have our reaction here, notice, so delta G0 is going to be the products, and the products minus the reactants. So my products are iron and aluminum, and then aluminum and iron oxide. And so to write it out, it would be the sum of 2 times the delta G0 of Fe plus 1 times the delta G0 of Al2O3 minus 2 times the delta G0 of aluminum plus 1 times the delta G0 of Fe2O3. Sorry about my writing here. Okay, and to plug in values then, iron is in its elemental form, so it'll be 2 times 0 plus 1 then. And look this up in the back of your textbook. Make sure you get these same values. But the delta G for Al2O3 is negative 1582. That'd be kilojoules. Minus, and then 2 times aluminum. Aluminum is an element, and so that will be 0. Plus 1 times Fe2O3. Again, this is a value that's going to be in the back of your textbook. Negative 743.6 kilojoules. So if you put all that in your calculator, the delta G of the reaction is equal to negative 838 kilojoules per mole. And we could say that the process is thermodynamically favored. Thermodynamically favored processes are not necessarily fast. Rust is a great example of that. So the rate is basically determined by kinetics, not thermodynamics. Oxidizing is a thermodynamically favorable process, but it can take several hundred years to kind of, for something to rust away. We talk about kinetic control. And what happens in these processes is there's actually usually a super high activation energy. And so the process may be exothermic, but have a very high activation energy. And if it's known that a certain process is thermodynamically favored, but it does not occur at a measurable rate, then you can safely assume that the process is most likely under kinetic control. And basically, we can use external energy. We're going to learn, in this unit, we'll learn about the use of electricity to drive non-thermodynamically favorable processes. And so we can, we'll study that. The other thing that can happen is that photons can supply the energy required to remove the electrons from atoms. And so photosynthesis is actually a great example of this. The conversion of CO2 and water to glucose, if you remember from studying photosynthesis, you have the light reaction and the dark or non-light dependent reaction. The purpose of the light reaction is to make ATP to fuel the synthesis of glucose. And so a great example of photons supplying the energy, an outside source providing the energy for a non-thermodynamically favorable process. Reactions can also be coupled together when the delta G is greater than 0. This is actually what happens in the metabolic breakdown of glucose. And so notice that the delta G of this is not a thermodynamically favorable process. And so what happens in the first part of cellular respiration, there is a conversion of ATP to ADP so phosphate. And the conversion of ATP to ADP is has a delta G value of negative 30.5 kilojoules per mole. And so this thermodynamically favorable process can be coupled with a non-favorable process. And we see that over and over again in metabolic systems. And so this concludes this part of the lecture, and I'll send you a message that will give you this video as well as your homework assignment. So hopefully this makes sense, but